You know, when you think about a mechanical ventilator, you think of a lifeline, right? A machine that literally breathes for you when you can't. But what if I told you that inside this life-saving process, there's a hidden force at play, one that can actually turn this essential tool into a source of harm? Let's dig into this.
It's a heck of a paradox, isn't it? How can a machine that's delivering the very air you need to live, at the same time, potentially damage the delicate tissues of your lungs? Well, this is one of the central challenges for doctors in intensive care units all over the world.
And this exact problem, this life-saving dilemma, it actually has a name. Understanding it is really the first step, because it gets to the very heart of how we use mechanical ventilation.
It's called ventilator-induced lung injury, or VILI for short. And honestly, the best way to get your head around it is to think of your lungs like a really, really delicate balloon. If you force too much air in, or you push it in too fast, you can stretch and damage the material. And that's basically what VILI is. It's the physical damage that the ventilator's power can inflict on the lungs.
Okay, so if this force is the problem, how in the world do you measure it? I mean, to protect patients, doctors need a way to actually quantify this risk. And the clue, as it turns out, lies in a concept called mechanical power.
Mechanical power, or MP, is a pretty brilliant idea. It takes all those different settings on the ventilator, we're talking pressure, air volume, breathing rate, the whole shebang, and it combines them into one single comprehensive number. This number represents the total energy being delivered to the lungs. Put simply, higher power means a higher risk of injury. It's kind of like a vital sign for lung safety.
But there's always a but, isn't there? The most accurate way to calculate mechanical power, the so-called gold standard method, involves some seriously complex math. It's just not practical for a busy doctor trying to make a quick decision right there at the patient's bedside. There had to be a simpler way.
And this is where new research comes into the picture, offering what could be a real game changer, a simple new formula to estimate this crucial number right there at the bedside.
It's called the M equation. The little m stands for mean airway pressure, and the big M stands for minute ventilation. Think of it as a beautiful, simple shortcut. Instead of all those complex calculations, it just uses two values that are already available on pretty much every modern ventilator.
So let's break down how it works. It's actually super straightforward. A clinician can literally just look at the ventilator screen, grab the mean airway pressure, and then multiply it by the minute ventilation. With a tiny correction factor, boom, they get a quick estimate of the mechanical power. It's fast, it's easy, and it really promised to be a fantastic tool, especially for patients who aren't breathing on their own yet.
But you know, medicine is rarely ever that simple. This raised a huge question. What happens when the patient is no longer passive? What happens when they start trying to breathe on their own?
This is such a crucial point. The moment a patient starts taking their own breaths, they're adding their own muscular energy into the system, so the total power being delivered to the lungs is now a mix of the ventilator's power and the patient's power. So the big question is, could this simple little formula still keep up?
To find out, researchers had to look at the two main ways a ventilator interacts with a breathing patient. In pressure-controlled mode, or PCV, the patient's effort and the ventilator kind of work together. But in volume-controlled mode, or VCV, the machine is set to deliver a fixed volume no matter what. This means a patient's own breath can actually cause the airway pressure reading to drop. Now hang on to that little detail. It's about to become very, very important.
So researchers ran thousands of simulations for both of these modes to test how accurate the equation really was. And the verdict? Well, it was surprising. It was really a tale of two very different outcomes.
First up, the good news. For patients in that pressure-controlled mode, you know, the one where the patient and the machine work together, this simple formula was a home run, a clear success.
Just take a look at the data here. In science, a perfect correlation is a 1.0. And as you can see, the formula's gas for the ventilator's power and the total power were almost perfect. We're talking correlation values above 0.96. Even for the patient's own breathing effort, the correlation was still really strong. The bottom line is, in PCV mode, this simple formula works like a charm.
But then came the results for volume-controlled mode. And this is where things get messy. This is where a crucial weakness was exposed.
You can see the problem immediately on this chart. Just look at that third bar. I mean, wow. While the formula could still estimate the ventilator's power pretty well, its ability to account for the patient's own breathing effort completely fell apart. The correlation just plummeted. It was basically blind to the energy the patient was adding. And why? Well, remember what I said? In this mode, the patient's effort can actually lower the pressure reading. and that tricks the formula. It thinks less energy is being used, when in fact the total energy is actually higher.
This really illustrates the study's main conclusion, which is captured perfectly in this quote from the research paper itself. The formula's reliance on airway pressure becomes its Achilles heel when a patient is breathing on their own in volume-controlled mode.
So, let's step back from the charts and the numbers for a second. What does all of this actually mean for patients' safety in the ICU?
All right, here are the big takeaways. First, the equation is a great, simple tool, but only in the right context for patients in pressure-controlled ventilation. Second, and this is the really important part, it is not reliable for patients breathing on their own in volume-controlled mode. In that scenario, it can dangerously underestimate the total power, making clinicians think the lungs are safe when they may actually be at risk. It's a powerful reminder that in medicine, one size rarely fits all. You have to use the right tool for the right job.
And this leaves us with a critical question for the future of medicine, doesn't it? The search for simple, elegant solutions is essential for progress. But as this research shows, we have to be incredibly careful to understand their limitations. The challenge isn't just finding a simple answer, but knowing precisely when, and just as importantly, when not to use it.